Hi class, this is Dr. Vev. I'm going to be solving an actual problem with numbers. So this might be familiar to anyone who has moved heavy boxes during moving day in your dorm. So let's suppose you have two boxes or two crates of mass capital M and little m. You have two options. Let's say you can push with a force P, which is 200 newtons here. And you're wondering whether it's better to push the big box or the small box. So think for a minute and think about moving two large boxes and just put some kind of thoughts in your mind about which is the better way to do it. First of all, will the accelerations be the same? The other important consideration is what about the force between the boxes? If the boxes have delicate things, you might want to minimize the force between the boxes. And then let's suppose that as you're pushing it, the floor suddenly becomes frictionless. Initially, the floor had some friction, given by the coefficient of kinetic friction, 0.3. And let's say as you move it across the dorm, the floor suddenly becomes smooth. Which of the answers will change and how? Assuming here that your pushing force does not change. So let's solve this problem. Solving for the acceleration in a combined mass problem is interesting strategy. It's always better to use the blob strategy. So I'll blob it, meaning that I'll consider the two masses as a single mass of mass m plus m. Let's look at the free body diagram acting on this combined blob. There's going to be the force of gravity, which is m plus m times g, acting down. There's the normal force, F sub n, and there's the pushing force, of course. And we have the friction force, which I'll call F sub F k. And the combined action of these forces is that it accelerates with an acceleration a. Now you can immediately see from this blobbing philosophy, it doesn't matter whether m is ahead of m or little m is ahead of m, the accelerations are going to be the same because it's only the combined mass that seems to matter, especially since the coefficient of friction mu sub k is the same for both boxes with respect to the floor. Let's write down the equations that we have in this circumstance. The first equation is the sum of all the forces in the y direction is 0 because the boxes don't fly. So that gives me the normal force is equal to the force of gravity. I also have the law of friction. The law of friction states that the force of friction, kinetic, is equal to mu kinetic times the normal force F sub n. Let's substitute this F sub n in there. So I get force of friction kinetic is equal to mu sub k times m plus m g. Then we have the equation in the x direction. Sum of all the forces in the x direction equals the total mass times the acceleration. I'll just write it as m capital T times acceleration, where m capital T stands for m plus m. So the forces are going to be P minus F sub Fk is equal to the total mass, which is m plus m, times the acceleration. Now what I'll do is I'll take F sub Fk from here and put it here. So I get P minus F sub Fk, I just did that, divided by m plus m equals A. Let me just write another equation, mu sub k times m plus m times g over m plus m. And now I'll substitute all the values, all the numbers that I've given here. So it's 200 newtons minus 0.3 times m plus m is 50 because I have 20 plus 30, but that times g, which is taken to be 10 in this case, not 9.8. So 50 times 10 is actually 500 newtons divided by the total mass, which is 50 kg. So that's going to be 200 minus 150, which is 50, divided by 50, and so that answer is just 1 meters per second squared. So that's the answer for the acceleration of the combined blob. Now, how do we find the force between the boxes? You have an option here to split up this blob. We can either look at the mass that's been directly pushed, or you can look at the mass that's trailing. The mass that's trailing is easier to analyze because there's just one force acting on it. So let's consider the trailing mass. So these are all important strategies in solving problems. The trailing mass, which is going to be different in both cases, here it's going to be little m and there it's going to be capital M. So rather than solve the problem twice, I'll just call it mass sub little t for trailing. But in this case, the acceleration is going to be to the right. There's the force between the blocks, which I'm going to call little f, the force of friction, kinetic, there's going to be the normal force, Fn, and there's going to be the weight, which is mtg. Well, exactly as before, let me try to partition this so you don't get confused. I'll block this off. The sum of all the forces in the y direction is 0, so I'm going to get F sub n equals mtg. The law of friction gives me F sub fk equals mu times F sub n, which is mu times mtg. And the sum of all the forces in the x direction gives me F minus F sub fk is equal to mt times the acceleration. So we can solve for little f. Little f is equal to, now F sub fk is mu kinetic times mtg, so mt is common, so I get mt times a plus mu sub k times g. That's our formula for the internal force between the two blocks. Let us solve it. Let's call that's case A and that's case B, so let's solve it for case A and case B. They'll turn out to be different. Here, keep in mind your initial guess as to which is more. So if the trailing mass for case A is little m, which is 20 kg, so in that case, F, the force between the two blocks, is going to be 20 kg times the acceleration, 1 meter per second squared, plus mu sub k, which is 0.3, times 10 meters per second squared. Now 10 times 0.3 is just 3, plus 1 is 4, so 4 times 20 is just 80 newtons. 80 newtons is the force between the two blocks if you push the heavier one. If you push the heavier one and let the lighter one trail. What happens if you push the lighter one and let the heavier one trail? Then mass trailing is capital M, which is 30 kg, and then F will just be 30 kg times everything else is the same. So this is going to be 120 newtons. So you can clearly see that pushing a light object, pushing the smaller object, is going to create a bigger force. So if you are pushing, let's say, a refrigerator and a TV, you would much rather have the refrigerator push the TV rather than the TV push the refrigerator. You can almost visualize the TV breaking up if you try to use the TV to push the refrigerator, whereas the refrigerator pushing the TV would just slide along. So that's kind of obvious in daily life, but it's nice to see the math confirming it. The second part of the problem is actually very interesting. The flow becomes frictionless. Which answers would change? Now if you visualize this example I gave you of moving a television and a refrigerator on a rough surface, and suddenly the surface becomes smooth, your thinking is almost certainly going to be that the moment I come to a smooth surface, these forces are going to decrease. because you would think that the friction is causing the TV and the refrigerator to jam up against each other much more strongly. Well, let's see. This is the beauty of physics. You don't have to guess. You can simply solve and see what happens. So I remove friction. Either you go from a carpeted floor to a smooth tile floor, or whatever the reason is, the floor becomes frictionless, which means that mu k is 0. Well, all I would have to do is go to my previous answers and put mu k equal to 0. So let's find out what happens to the acceleration. The acceleration here, if mu k is 0, I'll just get p over m plus m. Let's find out what that is. The pushing force is 200 newtons and m plus m is just 50 kg. So not surprising, you'll suddenly start moving faster. Because you're coming to a smooth floor, you're suddenly going to accelerate much faster. And let's now look at the what happens if the trailing mass is the smaller one. This time, the force between the two, you will put mu k equal to 0. So I'm just going to get m trailing times the acceleration. The trailing mass is 20 kg and the acceleration is 4 meters per second squared. The answer is still 80 newtons. So this should be a jaw-dropping moment for all of you. It doesn't matter if the floor is rough or smooth. The force between the two objects will not change. I'll talk a little bit about human psychology after I finish this problem. M sub t is equal to capital M equals 30 kg. Now, as expected, if this is counterintuitive, the next one is also going to be counterintuitive, and you'll find that it doesn't change. Mass trailing times the acceleration. The trailing mass is now 30 kg, but the acceleration has also become bigger. So that's going to be 120 newtons. It doesn't change there also. So what causes this? What causes this weird phenomenon that regardless of whether the floor is smooth or rough, the force between the two objects is the same? The reason why your guts will rebel against this answer is the following. If you are actually the one doing the pushing, let's suppose you're struggling to move something and you put a certain amount of force and it's going at a certain rate and it's going at a certain rate on carpet, and you suddenly come to the smooth floor, you're not going to continue pushing at the same pushing force. In fact, as you can see, it goes from 1 meters per second squared, which is kind of a controlled motion, to 4 meters per second squared. So what you're going to do is you're going to sort of cut back. You're going to not push with 200 newtons anymore. You're going to push with maybe 150 newtons or maybe even 100 newtons to bring the acceleration to manageable amounts. So in a real life situation, you will never do the pushing with the same push on both frictionless and frictionful surfaces, and as a result, this particular calculation might seem to be a bit jarring. In this particular case, in a situation where you have a robot pushing with a fixed pushing force, then you will always have the same internal force.